What happens in wireless neurostimulator calibration labs? Imagine a high-tech workshop where tiny devices are fine-tuned to work perfectly inside the human body. That's what happens in wireless neurostimulator calibration labs. These labs are essential for making sure neural implants work safely and accurately. The process starts with charge balancing. Technicians activate both the positive and negative current sources at the same time to check for differences. They measure the error current, which is the difference between the two, and then correct it. This step is repeated several times to ensure the biphasic pulses deliver equal charge on both sides. This prevents tissue damage caused by net ion flow. Next, calibration of digital to analog converters is performed. These components turn digital signals into precise electrical currents. Advanced systems use sub-binary radix digital to analog converters, which are calibrated automatically. Each calibration takes less than 9 seconds for a single converter. When calibrating a full set of 16 channels, it takes about 2 minutes and 20 seconds. Specialized equipment, like source measurement units, measure the current during this process. These measurements can range from microseconds to tens of milliseconds, depending on how precise the calibration needs to be. Technicians then verify the stimulation parameters. They check that pulse amplitudes stay within the set range, usually from 0.022 to 2 milliamps. Pulse widths are tested between 0.1 and 4 milliseconds, with increments of 0.1 milliseconds. Frequency settings are verified across 1 to 1000 Hz. Recovery pulses are calculated mathematically to keep charge balanced during stimulation. This ensures no excess charge builds up, which could harm tissue. Lead placement is also checked during calibration. Proper positioning of leads ensures electrical impulses reach the correct nerve fibers or brain areas. Misaligned leads can cause under- or overstimulation, sometimes requiring surgery to fix. To test this, technicians gradually increase current until they see muscle twitches, which show the nerve response. They find the lowest current needed for a response, called the motor threshold. Wireless communication is calibrated too. The implanted device must reliably receive commands. The system checks that signals are transmitted correctly and that the microcontroller calculates parameters accurately. Because microcontrollers discretize signals, slight variations can happen, so verification is key. Control signals are sent, sometimes modulated onto power signals, to activate multiple implants asynchronously. Safety checks are vital. Passive asymmetric pulse designs verify charge balancing by using reverse polarity pulses. These pulses are calculated to match the charge of the active phase, preventing charge buildup. Environmental testing confirms that devices work well even if wireless signals are temporarily lost. Technicians also verify that multiple implants are kept at least 8 centimeters apart to avoid interference. The lab environment is carefully controlled. Precise measurement tools, stable electrical conditions, and detailed documentation are all part of the process. These labs act as the bridge between device design and real-world use, making sure every neurostimulator is ready for safe and effective patient treatment.